let's start with what we know. We've talked about this man. His name is Isaac Newton, and the work that he did, of course. So far we've talked about just his laws of motion. And the last one was the third law of motion, which you know is also known as the law of conservation of momentum. So Newton found that mv is conserved for a system of objects. And now we call that momentum. So momentum is conserved. A couple of years after Newton published his results, a man by the name of Gottfried Leibniz came along, and he said that he had found that mv squared is conserved. Now this is so similar to Newton's work, but also different enough that people saw right away that there was a contradiction between these two. And most people agreed with Newton because, after all, he's Isaac Newton. So this idea was kind of forgotten for many, many years. Leibniz called it Vis Viva. He said Vis Viva is conserved, or the life force. Today we call that idea energy. And after 150 years of no one really doing anything with energy, a man by James Joule came along, and James Joule did some more research with the idea of energy, and he found that Leibniz was actually correct in his findings, and that energy really was a physical phenomenon that we can consider and should consider when solving problems or looking at the physical reality in our universe. Because he played such a vital role in this process, we have renamed the energy units after James Joule. So energy in the metric system is measured in joules. In America, we measure it in calories, and the metric system uses joules. So what does it actually say? So here's the stuff that we're going to be talking about over the next couple of weeks. There's two types of energy, mechanical energy and non-mechanical energy. We will spend most of our time talking about mechanical energy. Non-mechanical energy is just that. It's mechanical energy that's not anything to do with motion. It doesn't have anything to do with the stuff we've studied so far this year. So that includes sound energy, heat energy, chemical energy, and light energy. Those are all non-mechanical energy. They really exist, but we're going to spend most of our time talking about mechanical energy. And for the most part, we're going to ignore non-mechanical energy. There are two types of mechanical energy, potential and kinetic. And let me pause here and tell you that you can stop this video at any time if you need to slow down and get these things copied into your notes. In potential energy, there are two types. There's elastic potential energy and gravitational potential energy. We will, for the most part, ignore elastic potential energy. We're just not going to talk about it this year. That has to do with springs being compressed or stretched out. We're just not going to deal with that. We're only going to talk about gravitational potential energy. So potential energy is stored energy. You can fill that into the bubble on your notes. And gravitational potential energy has this equation: potential energy equals mgh. M is the mass of an object, g is on Earth 9.8, and h is its height. So an object, such as a person on a ladder, has potential energy. It's their mass times 9.8 times the height. Now the height you can define as whatever you'd like. So if I have a book holding it above a desk, if it's a meter above the desk, I can say the desk is 0 height, and the potential energy is mass times g times 1 meter. I could also define the ground to be 0 height. If I did that, then maybe the height would be 2 meters. So this is one of the great things about potential energy specifically, or energy in general. The problems that you solve with this can be as hard or as difficult as you want. There's usually a convenient h to define, but there's no right or wrong one. So I hope that you guys will find this much easier to solve problems than using projectile motion, the Porsche, the bulldozer, and then free body diagrams and all that stuff. Let's talk about kinetic energy for a little bit too. Kinetic energy is the energy of motion, and the equation for it is 1/2 mv squared. So an object has kinetic energy equal to its mass times its velocity squared. And you can see this is very close to Leibniz's idea of Vis Viva. Of course, he was off by this half, and that's part of what Joule's work confirmed, is that it was actually 1/2 mv squared. Well, how do those two relate to each other, and what do they have to do with each other? That's where this comes in. And I'm not going to give it away because you'll see, I think in a minute, we'll be able to figure it out. Energy cannot be created or destroyed. It can only change from one form to another. That is, whatever the system has, whatever energy a system has, it will always have that energy. This is just like momentum. And remember, for momentum, it was the law of conservation of momentum. For energy, it is the law of conservation of energy. Energy cannot be destroyed or created. It can only change from one form to another. Here's what I'm talking about. Let's go back to this chart and look at a sample, a really simple example to start. Let's take a ball, like a golf ball, and just drop it. As we drop it, it changes energy forms. At the top, it has all potential energy up here. It's not moving at all. It's some height, let's say it's this height, some height above the ground, so its potential energy is mgh. As it falls, it loses potential energy and it gains kinetic energy. You can think of it like this. At the top, it has all potential energy, no kinetic energy because it's not moving. Potential energy gets smaller and smaller. At the bottom, when its height is 0, its potential energy is 0. And that's when its kinetic energy is the highest. When we say that energy is conserved, we mean that the total energy has to be the same throughout this whole process. If there's 10 joules of potential energy here, there has to be 10 joules of kinetic energy at the bottom. And these two values would have to add up to 10 joules, and these two values would have to add up to 10 joules. Energy cannot be created or destroyed, only change from one form to another. A more complex example would be a roller coaster. In a roller coaster, they give you all your energy at the beginning through an electric motor or something like that. And then at the highest point, they let you go and you just coast. You have all potential energy here, and it changes to all kinetic energy down here, and then it changes to some potential and some kinetic, and then more kinetic and less potential, and so on. You just keep going round and round. The total amount of energy does not diminish throughout. It just changes from one form to another. Again, don't forget to check the website, my website, for this worksheet that you need to complete. I'll try to include a link down below in just a minute here.